Okay, now we're ready to talk about autonomous differential equations in a particular setting. We're going to start by talking about exponential growth, which is something that I hope most of you are pretty familiar with, but we're going to put it into the differential equations environment. Once we're done with that, we'll talk about the fact that exponential growth isn't really all that practical. It's not very realistic. It's not really what actually happens, but I'll come back to that. The way in which differential equations are useful in a population's setting, if you're looking at, for example, the number of bacteria in a petri dish and their growth changes over time, or their population changes over time. So we have population growth. We could talk about the half-life of a chemical, for example. In that case, we have population decay or population decline. We're used to seeing equations like this: y equals k e to the rt, where if I tell you that the rate of growth of a population, that might be 0.38, that would be 38%. T is the number of years, so T is time. K is the initial population. And y is actually a function of T. Y is equal to, we'll call it P of T, population in terms of time. Well, where does this formula come from? By now, I hope you'll appreciate that we can take a differential equation if it's in a particular form and solve it to come up with this equation. But where do we get the differential equation? I mean, if this is the equation that came about by solving a differential equation, then where did the differential equation come from? Well, when we're talking about populations, it's important to realize that the growth of a population is related to the number of individuals in the population to begin with. So if you start recording the population of red deer, say on January 1st, the year 2000, that's our time zero, then when we look at the population again later, we'll be able to compare them, but we know that population isn't linear. So we need to take into consideration the fact that the population at the later time is to a very large extent dependent on how many individuals there were in the population at time zero. In other words, if we had 100 deer in the population at time zero, we might have 110 later on. Whereas if we had 500 in the population at time zero, we're more likely to have 550 at the later time. And so it's not just a linear relationship, the population at time 2 minus the population at time 1. It's more accurate to say the rate of change is proportional. It's proportional means it's dependent on the population at the starting time. So what we say then is that the change in the population with respect to time is proportional, some constant, times y. And this is how we express changes in population. When we solve this differential equation, we're going to get the solution y equals some y naught value times e to the rt. And I hope you'll recognize that this y naught value here, it's y naught. It's the 0th value of y. It's an actual value. It's an actual constant. We just don't know what it is yet. And that's my k from up here. If you need to be reminded how taking a differential equation like this and solving it turns into an equation, a solution like this, then you might want to go back to some of the earlier videos. And in fact, in the video immediately before this one, I did a quick recap of how that comes about. So the solution to this equation is this equation, depending on what your y naught value is. So it's actually quite important to include here that we're going to say at time zero, the population is usually some known value. So this is a generic explanation of how the solution, how the exponential function came to be the solution of a differential equation, and how this differential equation came to be how we can represent our interest in the change in a population over time in the first place. This y right here is our p of t, right? This is our function p of t, and that's equal to a constant e to the rt. And you'll notice that if r is positive, you'll get functions that look like this. And if r is negative, use a different color, you get functions that look like this. So if the rate of growth is negative, then we have negative growth or decline of the population. So that's where this formula comes from that we're so used to from all the way back in algebra. We've been given this exponential growth function. The problem with this model is that it's not accurate. I want you to imagine, let me erase my graph here. Imagine that you have a petri dish with, say, 100 bacteria in it. And let's say that every hour you come back and check the population of your bacteria. Well, at time 0, the population is 100 because that's how many you put in the petri dish to start your experiment. After 1 hour, I don't know, we'll just pick some random y values here, and we're going to imply by our graph that our growth is somewhat exponential. It keeps getting, for each hour, it keeps getting bigger and bigger and bigger. Except that eventually the petri dish is going to be too small for the bacteria, and some of them will start dying off. So while some are still reproducing and creating more for the population, some start dying off. Either they run out of food or they run out of space. We call this the logistic equation. Well, we call this graph a graph of a generic logistic equation. There's a place here, we don't know what that is yet, we'll talk about it in a minute. The y value here for which the population cannot exceed. Right, so this becomes asymptotic up here in the same way as an exponential is asymptotic down here. This line, or this value, let's call it y equals k. This is our equilibrium solution. It's one of them anyway. The other one is down here. In this context, this is often called the carrying capacity. I have to be careful because apparently I can't write and talk at the same time. The carrying capacity, if you imagine, I'd like to talk a little bit about some vocabulary here. Here is a tank, and you can fill this tank with water. This tank is right now empty. You could fill it with water, and it would look maybe something like this. And let's say that when you filled it with water, it could hold 100 gallons. That means that the volume of water, the amount of water in volume in the tank is 100 gallons when it's full. When it's empty, I don't know if I can do this, take out the water. Let me just make an empty tank. When it's empty, the volume of water is 0 gallons, but the capacity is still 100 gallons. The capacity is how much it can hold, whether it has anything in it or not. Okay, and so the same thing is true of our carrying capacity. This is the amount of population, this is the largest amount of population that our situation can endure, whether or not we start with 100 bacteria in our petri dish or none. If we start with none, then clearly we're not going to have any population growth because there's no population to grow. But the capacity stays the same. It has to do with the growth rate has to do with how many and what type and whatnot bacteria we choose to put in there, the food we give them, and all kinds of other elements need to be taken into consideration. But for that type of bacteria in this size of petri dish, the carrying capacity will be whatever number it is, regardless of at what point in the experiment we are, right? Even before we start the experiment, the carrying capacity will be this number. That's the amount of bacteria that this petri dish can hold. Okay, that's enough for our vocabulary lesson. And I'm going to erase my graph as well because I want to leave it on the page, but it's a little too big. So I'm going to erase this and come back in and draw a smaller one quickly, so we have something to refer to. You'll notice that when I start graphing this, it looks like it's going to be exponential. And in fact, some of them, let me back up a little bit, some of them actually do look very much like they're going to be exponential, and then they just level off. That is a leveling off. That's not super accurate. Let me just tidy that up. There we go. So we have an asymptotic function at this point here, as well as down here and off to negative infinity. If I want to modify my differential equation so that it is more representative of what's actually happening here, which is logistic growth, I'm gonna rewrite it down here. dy dt equals ry, and then I'm going to modify it. But what I want to do is I want to find something to put in place of r so that near 0, it still looks like r. But as we go up the y-axis, as y gets bigger to a certain point, we can see that our function is growing here, and in fact, our curve is concave up. And it's reaching an inflection point here. Let's try to sketch one in. Looks like it might be about there. And so my curve is increasing, and up to about this point, if you couldn't see beyond t equals whatever this is here, let's put a mark there. We'll call that t1. If you couldn't see beyond t1, you might say, well, that looks like it's going to be an exponential graph, right? Up to that inflection point. Beyond that, my graph is still increasing, but it's doing so more slowly. So the change here is positive. The change here is also positive, but the second derivative is negative, right? Here I'm concave up, here I'm concave down. So what I want to find is a function that I can replace r with that has those properties. And it turns out that such a function can be written as, I'm going to erase r, and I'm going to rewrite it as r minus ay. I'm going to rewrite that. It's too cramped. This was my r minus ay times y. This y right here is this y right here. Notice that when y is 0, this expression here is r, right? So I still just have ry when y is 0. And in fact, when y is close to 0, when it's very small, this behaves very much like just r. So that's why we get this exponential curve here that behaves like the exponential function. But as y gets bigger, it overtakes r, and I then get r is always going to be greater than 0, and so I have a positive number minus another positive number. When this number is small, r overrides it, and it keeps this form here. We have the exponential looking function. But as this value ay, specifically y, gets bigger, then now I have a positive number minus a larger positive number, which is a negative number. So I have negative y. And remember, this is a rate of change. So that's why I have this concave down appearance. A is just a constant, and what it is will depend on the particular situation. So if this is a particular type of bacteria, A will be one value. If it's a different kind of bacteria, or the petri dish is larger or smaller, or there's a different kind of food for the bacteria, then A will be a different value. If we're looking at the population of red deer or rabbits or sharks, then A will be a different number because the situation calls for that. Now I'm going to do just a little bit of algebra. This, by the way, is called the logistic equation, or let's see, the Verhulst equation. I had never actually heard it called that before, so that just shows you I don't know everything. Boy, that's an understatement. So this is apparently called the Verhulst equation. Pierre Vulhurst lived between 1804 and 1849, was a Belgian mathematician. And he introduced this equation as a model for human population growth. And it became known as the logistic equation. But I'm going to do some algebra now. I'm going to say what happens if I factor out the r. Well, I'm going to get 1 minus ay over r. times y. And then I'm going to say, I'm going to write this as y over r over a. Bear with me. Lastly, I'm going to let r over a be called k. And that gives me dy dt equals r times 1 minus y over k times y. And this is our logistic equation. We actually had it before. We had the logistic equation here. Where am I? Yes, here. But it's convenient to write it this way for a couple of different reasons, neither of which will be particularly obvious just at the moment, but should become obvious as we move along. I will point out that K here is this carrying capacity, which is why I used K on the previous screen. That's the carrying capacity. We will come to know R as something called the intrinsic growth rate. R for rate, just like it was up here. This is the same R, by the way. Remember, it comes out in this form here. It's the same R. It's the intrinsic growth rate. It's the rate at which this population would grow if there were no limiting factors. In the previous video, we looked at what solutions to an equation like this look like graphically. I'm going to do that here now as well. There are a couple of obvious things we want to consider. If this equation has a solution y equals a constant, I'll just write y equals c, I guess, for now. If y equals c, then the derivative of y with respect to t must equal 0. So if we want to start finding some representative solutions for this thing, we might start by saying, where's the change equal to 0? That will give us all the values of all the functions y where the answer is just a constant. Okay, so the first thing I'm going to do is I'm going to take the right-hand side here and set it equal to 0. I have I have r times 1 minus y over k times y. I'm going to set that equal to 0. And that tells me either that r equals 0, y equals 0, or 1 minus y over k equals 0. And that means that, let's see, if I multiply both sides by k, I get k minus y equals 0, so y equals k. So I have three solutions to this equation, y equals k, y equals 0, and r equals 0, but we're not interested in that one because this is not a solution to the differential equation dy dt equals, I mean, it's an answer to this equation, right, in that r equals 0 satisfies it, but it tells me that the growth rate is 0. So it's a trivial case. It's a completely uninteresting situation, at least from a mathematical perspective. If the growth rate is 0, biologically, there may be a reason for that. And so in that case, if you're doing this to study biology, then there's a good reason that you might want to know why r equals 0. But mathematically speaking, we have two solutions. And those two solutions are, I'm going to make my pen a little bit bigger here, y equals 0 and k equals 0. Sorry, y equals 0 and y equals k. So now I have, right, I have those two lines, and those are the equilibrium solutions, right? These are, let me write them down here, y equals 0 and k are the equilibrium solutions. Now notice that another way to write this equation is as dy dt equals r times 1 times y minus r times y over k times y. And that means that this is a quadratic. Moreover, it is a negative quadratic, so it's going to have this kind of shape. We have one of our solutions at 0 and the other one at k, so I'll plot those in. We have a negative quadratic with roots of 0 and k. I've drawn this a couple times now, and I can either erase or I can just undo, and if I undo, you don't get to see what I drew in the first place, and that's probably a good thing since I'm having a hard time drawing it. There we go. This is a quadratic, a parabola, inverted parabola, and its vertex is its vertex is halfway between 0 and k, so it's at k over 2. And if I plug k over 2 into my equation, either this version of it or this version of it, I get for my output r times k over 4. So my vertex there is at k over 2, comma, r times k over 4. That's that point there. Now remember that what I'm sketching a graph for here, not very well, but what I'm trying to sketch a graph for here is the differential equation, not the solution. The solution, we don't have an equation for it yet, but the graph of that solution is going to look something like this. The graph of the differential equation, before I solve it, that graph looks like this, and that tells me something about y, right? It's really tempting to make this a t-axis, but it's not, it's the y-axis. It tells me something about the function y. It says that, among other things, between 0 and k, dy dt is positive. The rate of change of the function y, which will ultimately be a solution to this equation, is positive between 0 and k. I should add to my graph here a little bit. I'm going to need that in a minute anyway. So between 0 and k, dy dt is positive. I'm going to indicate that with an arrow that goes between 0 and k and shows that it's increasing. Now, we often do that, we usually do that, in fact, on a vertical axis. We have 0, let's see, let me relabel that a little bit. Let's call that 0, and that one k. I'll make it a little bit taller. And I would say that between 0 and k, y is increasing. Okay. After y, once we get beyond, after k, once we get beyond y equals k, which would be up here in this version, but it's over here in this version, y is negative. So for values greater than k, y is negative, which means my function is decreasing. If the rate of change is positive, the function is increasing. That's calculus 1, I think, differential calculus, right? If the rate of change is negative, then the function is decreasing. Okay, now I'm going to go back to my function, my graph of the derivative of y, the graph of dy dt, and I'm going to look at the values of y near t equals 0. And the values of the derivative are small. This is the derivative graph, right? The values of the derivative are small, which means the slopes near 0 are all going to be small, but they're all positive. The same thing happens at k. The values of the slope, this is the graph of the slope, it's the graph of the derivative. The values of the slope are all going to be small, but in this case, they're negative. So I'm going to add some little indicative lines to my graph up here. I'm going to turn it into a slope field. I sort of feel like I should erase this curve here because for this particular function, it may not be accurate, but I'm going to leave it there for now just to sort of prove to you, if anything, that the situation that we're in here, where the growth is capped in some way, limited in some way, does produce a graph that has this shape. So going back to the things that we learned in the previous video, values of y near 0 and near k are positive. So the little slope indicators that I put here near 0 and near k will be positive, right? But they're all very small values, right? They're close to the y-axis here. They're close to the the horizontal axis. So they have numerically small values, but they are positive. So let me add some of those in for you. Now, some of these look a little too big for me. They look like they're approaching a slope of 1, and that's actually a little too big, but it's really kind of hard to draw little lines like that with slopes smaller than that. So I'll just leave them. Now what I want to look at is values of y between 0 and k. As I get closer to k over 2, let's put k over 2 on the map here. This is k over 2. And in fact, I think I'm going to put a little dotted line in here just to help guide my hand when I do the next step. As I get close to values of k over 2, I have very large positive slopes. So when I draw my lines in here, they're going to be very steep. And they are also going to be positive on both sides of k over 2. So let me do that. Okay, so there's those ones. And then in between, I'll go between 0 and k over 2. I have slopes. Remember, these values here represent the slope. For values of y between 0 and k over 2, values of y between 0 and k over 2, I have slopes that are larger than 0, but smaller than the maximum value here. So in between 0 and k over 2, I have positive slopes that are getting bigger. And between k over 2, I have positive slopes that are getting smaller. So I'll add a few more of those in. Okay, so for y values between 0 and k over 2, my slopes start small, get bigger and bigger and bigger as I approach k over 2. Down here, and between 0 and k over 2, I have values for my slope. This is the graph of the slope that start small. They're all positive, but they get bigger and bigger and bigger until they get to k over 2. As I go away from k over 2 towards k, my slopes are going to stay positive, but they're going to get smaller and smaller and smaller. So I'll add those ones in. Okay, I think it's starting to take shape. You can see that if I pick a point, grab a slightly thicker pen here. If I pick a point, say here, then as I start sketching and meet the slopes as I go along, they pretty much sketch out the shape that I predicted would happen. There's one thing we haven't done yet, though, and that is to look at slopes down here, slopes of y, the function y, for which y is greater than k. So we're down here, we're looking at y values bigger than k, and up here we're looking at y values bigger than k. So up here, what I have here is all of my slopes. This is the graph of the slope. All of my slopes are negative. My slope values are negative. They start small and they get bigger as we go higher and higher on y. So I'm going to graph some negative, small, and then increasing slopes in my slope field as well. Okay, my software that I use for this won't let me graph up here because there's there's a button in the way. So I can point to it now by starting down here and moving my hand up, but I can't actually start. Anyway, I can't graph up there. But you can see that there as well, if I start graphing here and follow my slopes, I get a curve that looks something like that. Now, something else I'd like to point out here is that k is an asymptote, right? These are equations that behave like the exponential function. And in fact, I have not drawn it very well here, but this graph would look kind of more like this one, right? And this one, that one's not too bad. That's asymptotic. K is an asymptote. And so if I find a solution, say I've got one that starts here. I've got my buttons are in the way again. Hang on a second. Let me change something real quick. There we go. If I start, find a solution that sort of starts way up here, Get my pen to work now. There it is. And comes down like this. It will be asymptotic, but because it's asymptotic, that entire solution is above the line y equals k. So the entire solution exists in this interval. If I find a solution, different color pen here, if I find a solution that starts here and follows this path, then that solution will always only exist in the interval 0 to k, the entire solution, because k is an asymptote. Something else that's really kind of cool is, I'm running out of colors. I guess I'll stick with white for now. We can find this inflection point. We can determine the concavity of our solutions, because the concavity is decided or determined or calculated by taking the second derivative of the function, right? Well, we don't know the function, but we have its first derivative. It's this thing right here. That's the differential equation we started with. So if we take the derivative of this and set it equal to 0, we'll know what our inflection point is. How do we take the derivative of a function with respect to t if there's no t in it? Well, we can use the chain rule to do that. So I'm going to rewrite this as, get a better size of pen. I'm going to rewrite this as, I feel like I need to erase something. I'm just running out of room. I think what I'll do is erase this quadrant here, and I'll do my work up there. Okay, recognizing that what I want to do here is take the second derivative of y with respect to t. I can start by rewriting that as the derivative with respect to t of the derivative of y with respect to t, right? The derivative with respect to t of the function y. Now take the derivative of that with respect to t. That's what I'm doing here. And the derivative of y with respect to t, so I'll rewrite this again, d dt of some function of y, where this function here is, it's a function, but it's a derivative with respect to t, right? It's kind of like saying, if y is f of t, then this would be f prime of t, but I'm leaving it like this so that it's consistent with your textbook. That is equal to, because it is still a function, right? Just because this doesn't have a prime on it doesn't mean it can't be derivative. There is a function which is a derivative of another function, and that's what I'm calling this f. Now that is equal to, I'm going to use the chain rule here. This is the derivative with respect to t of a function with respect to y. So my main variable in this function here is y, but I want to take its derivative with respect to t. Remember that t is embedded. I could write this. Let me do this. I'll write this as f of y of t. And so when I take the derivative with respect to t of that, I'm going to get the derivative of f, which is f prime of y, times the derivative of y, that inside function there, with respect to t. And this I can write as f prime of y times, now dy dt, we go back down here, that's my primary function, that's my solution, so I'm going to call that f of y. Well, that is f of y. Now I'm looking for concavity here, and the concavity is determined by deciding where, or finding where, the second derivative of a function is positive, in which case it's concave up, and where it's negative, in which case it's concave down. So where is this thing positive? Well, we have a product here. So I'm going to observe that d squared y, or dt squared, is greater than 0 when f prime and f have the same sign. And it's negative where they have opposite signs, where one is positive, either one, and the other one is negative. So where is, I've got my pointer ready here, but I'm not sure what I'm pointing at yet. dy dt, which we're calling f of y of t, right? Where is this thing positive? It's positive between, for where y is between 0 and k, where y is between 0 and k. So this is positive where y is between 0 and k, and it's negative everywhere else. We want these things to have the same sign, so we need to also know where f prime is positive. And we can also determine that from our graph down here, because if this is the graph of the derivative, the graph of the second derivative, remember that the derivative is f of y, and the derivative of the derivative is f prime of y. The derivative of this graph is the second derivative. The derivative of this would tell us where the slopes at various different points. We can tell that the slopes are positive between 0 and k over 2, but negative between 0 and k. So we have positive slopes for y between 0 and k over 2. So where these have the same sign, or at least where they're both positive, is only between 0 and k over 2. And so that is where the functions are, the solution y is going to be concave up. And as you can see, that is the case. This graph goes from 0 to k over 2 in a concave up manner, and then after that it switches to concave down. This is where these graphs are positive. F prime is negative between, let's see, it's going to be negative between k over 2 and infinity. So this will be, let's just call it y greater than k over 2, negative. That's where this graph is negative. That's where this function is negative, is where y is greater than k over 2. So from here on. And this one, let's see, the original graph, right? The original graph, it's only positive, the derivative, the dy dt, is only positive between 0 and k. Never is it positive again. So that means that never, once we go from concave up to concave down at k over 2, we're never concave up again. So that just verifies that this graph is the right shape. Okay, one more sort of observation here, and then we're going to change tack a little bit, but I do want to point this out because I think it's really quite interesting. This logistic curve here is made up of this blue one, or the first one I graphed, maybe here, this thin white one here. Any of these really, you could look at those and say those are sort of a typical logistic curve. That's the shape that a logistic curve takes. But what's interesting about the whole graph is that you're starting here with some population greater than 0, and you're letting it grow unbounded except for environmental conditions, which cause it to be, its growth to be restricted at some point. We've talked about that. We call that value the carrying capacity. Your textbook uses the environmental carrying capacity to describe it. It's also called the saturation level. If you imagine salt in water, then saturation is when you've got so much salt that the water can no longer absorb it, right? That's when it's saturated. And just like anything else, there's a moment in which that happens. There's an exact value at which that happens. And in this case, that would be K. But what happens if you start with a population of, say, 10 and let that population grow in its environment, subject to the restrictions of the environment, is like this blue curve here. That's the kind of growth you'll see. It will continue to grow, but is severely restricted as its numbers get very large. What's particularly interesting to me about this model, though, is that if you start with a population above the carrying capacity, in other words, if a field can sustain a population of deer as long as the population is less than 100, and you drop 150 deer into that field, there's not going to be enough food. You know, they may reproduce, but they're going to be dying off at a faster rate than they can replace their own numbers. And so their numbers will still approach this carrying capacity, even if they start above that value, and perhaps particularly if they start above that value. I just think that's really quite interesting, and frankly, I think the graph is beautiful as well. It's probably just me being a weird math person, but I just think that that's a really interesting thing, and it's not something that we really talk about very much or very often in this context. You know, we're here to learn how to solve differential equations, but what do they mean and why do we use them in the first place? And that's really just one example. But this particular section specifically, I think, does a really good job of explaining how to approach a problem like this, how to determine what the shape of a graph is, but also why we would want to know in the first place. I just thought of something else I kind of wanted to tack on here before we move on, and that is that we talked about this a little bit in the previous video, but I'm going to bring it up here again. K is called a stable equilibrium value, and y equals 0 is called an unstable equilibrium value. And just as a reminder, what that means, you could particularly see either by the phase diagram or the phase line or by the little line segments of slope, representative slopes that I drew in here. As when we're looking at those little lines close to K, or if we do it on the phase line here, we can see that they're approaching K, right? They're moving towards K. Our growth is positive when we're close to K below it, but negative when we're close to K above it. In both cases, they're sort of pointing to the line y equals K. So we call that an equilibrium. We call that a stable equilibrium because we're always moving towards that number. If you drop 100 deer in a field and the carrying capacity is 1,000, then when we get to close to 1,000, we're going to approach 1,000 and not go any higher. Or if you drop 1,500 deer into that field, then some of them will die off and we'll still approach the population of 1,000. So this is called a stable equilibrium. Whereas y equals 0 is called an unstable equilibrium because our slopes are moving away from it. Right? If you drop 100 deer in a field that can support 1,000, guess what? They're going to have all the food they need. They're going to reproduce very quickly. And again, short of some other restriction like a disease that wipes them all out, they're going to reproduce and they're going to reach that capacity. There are two equilibrium solutions here, or two equilibrium values, but the curves move away from the bottom one down here and towards the top one. So y equals 0 is called an unstable equilibrium, and y equals k is called a stable equilibrium. Okay, now we really are going to move on. But on the next slide, what I'm going to be talking about is a very similar looking equation to this carrying capacity equation that we've been talking about, which, although it looks very similar, has very interesting ramifications to the graph of the potential solutions. So on the next slide, we'll talk about something called threshold.